All right, so we'll be covering T3 and T4 today. These are pretty short sections. T3 specifically deals with electromagnetic waves, characteristics and properties of radio waves, and we'll talk about propagations of different bands. So we'll go ahead and start with UHF and VHF. UHF and VHF are in the, let's go ahead and switch it here. Yeah, I'll switch it back to my little whiteboard here. So remember, I have a cursor? I do not have a cursor. Oh my, why are you so slow? There we go. VHF and UHF, which are around, basically we'll call VHF everything above 50 megahertz or so is where we're concerned. It's technically anything above 30 to 300 megahertz. Oops, there's an M in there. And we're particularly interested in these because these have relatively short wavelengths on 150 megahertz, right in the middle of the VHF band. We've got a 2-meter wavelength. And with UHF, 70 centimeters, the UHF does a very good job of reflecting off of building surfaces and penetrating walls. But it is generally line of sight. So, question 1 in T3 is, should another operator report that your station's 2-meter signals were strong just a moment ago, but now are weak or distorted? Generally, the way you'd solve that issue is moving a few feet to the left or the right, because what can happen on VHF is something called multipath distortion, where you have your transceiver, or transmitter in this case, and it's broadcasting relatively omnidirectionally. But if we set up an obstacle, like a building or a mountain, things like that, where a signal might get bounced off and reflected, and then it might get reflected by something else again. This extra distance that this reflected signal has had to cover, coming back, will be far enough out of phase with the original path, with the shorter path, that it will mix and cause distortion. So generally, in a lot of cases, weak signals can be solved simply by moving a bit to the left or the right, or gaining altitude. Generally, the further you can get an antenna off the ground, the better time you're going to have communicating. And question 2 with UHF. UHF is generally used when you're in buildings, in particular at conventions and things. We pick a UHF simplex frequency because it handles inside of big concrete buildings much more easily than on VHF. And the reason is because the wavelengths are shorter, whereas with longer wavelengths, we have something like, I don't know, a mountain. Longer wavelengths can get over the mountains a bit more easily. Cover obstacles like that. Alright, let's switch it back here. Again, not sure how well it'll handle this in the recording. Suppose that'll remain to be seen. 3. Horizontal antenna polarization is normally used for long-distance weak signal, CW and single sideband contacts using on VHF and UHF. The reason has to do with the way radio waves interact with a ground plane. And switching it back here. So with antenna polarization is determined by the orientation of the electric field. If you remember, an electromagnetic field is two parts, the electric part and the magnetic part. And so depending on which way an antenna is oriented, either vertically or horizontally, will determine the orientation of the electric field, and we call that polarity. So a vertically polarized antenna will have a hard time listening to a horizontally polarized transmitter, because the electric fields are perfectly 90 degrees, perfectly perpendicular to each other. So generally, for single sideband and CW, we'll use horizontal polarization, also AM, especially in VHF, UHF, whereas vertical polarization, generally with FM. So polarization is important and is determined by orientation of an antenna. All right, let's see. All right, number 5. So so far, when we've talked about antennas, we've generally been talking about isotropic radiators, basically just an antenna that radiates in all directions. But there are certain types of antennas which direct which way the RF energy is directed. Directional antennas, like Yagi's, which focuses radio waves in one direction. And so in cases where there's, for example, a distant repeater, it's usually easier if you're just trying to get into that repeater at a good distance with as little power as possible. You want to use a directional antenna. And on VHF and UHF, because it is generally line of sight, we can use obstacles such as buildings to our advantage to reflect our highly directional signal to access a repeater right. And in a lot of cases, when operating mobile, you can hear when someone's operating mobile if they're on the fringes of FM coverage, for example, due to an effect called picket fencing. It's exactly like it sounds like. If you imagine a series of obstacles like a picket fence with gaps in between, and a moving transmitter, then our signal might sometimes be obscured by buildings, trees, etc. And might sometimes be relatively in the clear. And you can hear it. It sounds just like if you were to drag a stick along a picket fence, fluttering and fluctuating like that. So we call that picket fencing. And number 7. Surely we know number 7. Number 7's pretty simple. Electromagnetic waves carry radio signals between transmitting and receiving stations. We're generally always dealing with electromagnetic waves when we're dealing with radio communication. Technically, there are other modes of communication, but they're not exactly regulated by the FCC. For example, light. We can use lasers or high-powered infrared lights to communicate visually over line of sight distances. But generally, we are always talking about an electromagnetic wave. Like that. When we're carrying radio signals. And we had talked about multipath distortion just a few minutes earlier. Sometimes it doesn't always have to be a physical obstacle. In some cases, it can be an effect of the atmosphere. Ionospheric reflection, since with omnidirectional antennas, we're throwing radio waves all the way up in all directions. Sometimes they will be reflected back by certain atmospheric conditions, which can create a multipath effect because that signal's traveled further then the signal that the receiving station would get directly from line of sight. Yeah, let's use a different color here. And so a signal arriving from different paths, and this could be, since this is in many different directions, when they finally recombine, we can end up with some irregular fading, and that is caused by atmospheric reflection, and the signals, the reflected signals, recombining, arriving at different paths. All right, so for the world below 50 megahertz is our magical frequency. Oops, supposed to be an M there. We get some interesting atmospherics going on. Let's say we have our HF station here. For VHF and UHF, the atmosphere is transparent at those frequencies, so those just continue on forever and ever, traveling speed of light. Oops. Whereas transmissions at what we call the critical frequency, which is right around 50 megahertz, will start to be reflected back by different layers of the atmosphere. At 50 megahertz is not very pronounced, but everything below 30 megahertz will be reflected back. Let's get that coming. Will be reflected back at some point or another in different layers of the atmosphere, depending on the frequency involved. And these are generally 30 mega. Let's see. This is very low frequencies. This is 40 meters. This might be 20, 10 meters. Going up in frequency like that. And there is more than just vertical. We talked about vertical and horizontal antenna configurations and polarizations. There is also elliptical polarization, or kind of difficult to draw a phased array. Broadcast FM stations are circularly polarized. That way you can, on your car antenna is generally vertical, but at home you might use a horizontal dipole, and it'll receive FM broadcast stations just as well. But when dealing with skip propagation, like this, the signals that get refracted back from the ionosphere will generally not have the same polarization as when they left. They will be elliptically polarized to sort of a corkscrew. Or an oblong corkscrew at least, shape. And a side effect of that is on the receiving side, you can hear both vertically and horizontally polarized signals. So any antenna configuration should be able to receive elliptically polarized skip signals refracted from the atmosphere. Skip happens when signals are refracted and reflected by the ionosphere. And when the ionosphere is excited, we can hear distance stations. We refer to as dx, distance. We can hear stations from, depending on the frequency, thousands of miles away, depending on atmospheric conditions. And because it's so, the atmosphere is constantly changing, it'll cause the polarization to fluctuate back and forth. That's where we get that elliptical polarization from, which will cause the signal to fade in and out. So we might be hearing a station strongly at one point and then have it fade out again during skip propagation. All right, and now we're on, let's see, number 10 here. Error rates on digital transmissions are likely to increase when you're dealing with signals propagated over multiple paths. The same with the any multipath issue, because when these signals recombine and they are slightly out of phase with each other, we'll end up with some significant distortion. And so generally with any mode, but especially data modes, we can deal with that. Some data modes have ways of dealing with corrupted signals with checksum, or at least being able to check if the data it received was correct. And number 11, we were talking about the ionosphere and its role in skip propagation. The ionosphere is the part of the atmosphere which enables propagation of radio waves around the world. And there's different layers of the atmosphere, of the ionosphere, excuse me. That's awful. At the very top, actually, let's start with the bottom layer of the ionosphere. Is a region created by excitement from the sun's UV rays. And at the very bottom is the D layer, or the daylight layer. Directly above that, we have the E layer. And these both are directly dependent on excitement from the sun. So okay. And above those, we have a region of the ionosphere called the F layer. During the daytime, there are two F layers, F1 and F2. And at nighttime, these two combine into one layer. And each layer plays a role in which frequencies get refracted back or reflected back. Starting at the bottom layer takes care of everything around 7 megahertz. I don't think you'll need to memorize these exactly, but you do need to be aware of its existence. We call this skywave propagation. And it is enabled by the ionosphere. How am I going to write this? All right. And I think we touched on it before. The name of the distance that a radio wave travels during one full cycle is a wavelength. So from here to here, this is one cycle. Or one wavelength. If it gets confusing, sometimes it can be. At this point, this is measured from positive and negative cycle at the origin crossings, which can be a little confusing. An easy way to think of it is looking at a wave like this. One cycle is the distance from one peak to the other. So this distance here is one wavelength. And we abbreviate wavelength with a lowercase lambda. But one cycle or one wavelength works. And it is also a physical distance. Wavelength is a measure of distance, which is measured in meters. And of course, since it is an electromagnetic wave, we do have an electric field which determines the polarization. The electric field is always perpendicular, so 90 degrees. Let's choose a different color here. Is always 90 degrees perpendicular to the magnetic field. And in free space, this is traveling at the speed of light, which is 300, let's see if I can get this right, 300 million meters per second. Blazing. 300 is an important number because we can relate the velocity of a wave with its frequency and wavelength. Frequency is the number of cycles it completes in 1 second. So a 1 Hertz wave is 1 cycle per second, which is a positive alternation and a negative alternation, or the distance, or the time, excuse me, from one peak to the other. And since radio waves travel at the speed of light, we can plug that into our equation. Lambda. So this is an inverse relation. As the frequency increases, wavelength decreases, gets shorter, and vice versa. And so an easy way to do this calculation is 300, you will need to know this, 300 equals lambda f, or where the frequency in megahertz. It works out this way because a megahertz is the prefix mega, gives us a million cycles per second. And so that works out to be 300 So for example, let's say we have a wavelength of 2 meters. We want to figure out what a frequency on 2 meters is. That's a pretty simple operation there. Divide both sides by 2. We end up with a frequency of 150 megahertz. Or the other way around, we can start with the frequency and solve for wavelength. So say a frequency of 30 megahertz. Divide both sides by 30. Oops, not what I meant to do there, but oh well. We end up with a wavelength of 10 meters. Right, now we're on in T3B7 at this point, just as a reference. Do you have any questions so far? I don't think so. Don't have much of an audience. That's all right. Keep recording. The property of radio waves is identified by different frequency bands, different frequency ranges, or the approximate wavelength. Generally, we talk about the wavelength of a band, so 2 meters, 40 meters. Etc., etc. The frequency limits of various ranges, particularly VHF, is, as we mentioned before, from 30 megahertz to 300 megahertz. Below that is HF, from 3 megahertz to 30 megahertz. And UHF above that. These are all in related by 3. And you'll need to know this one. Oops. That wasn't very good. You want to know this one for an exam question. Actually, you're going to need to know VHF and UHF. And HF. Oh, I covered all the bases. There you go. I'll go ahead and show this graphic here. That's, oops, that is not what I wanted. There we go. We see here the certain portions of different wavelengths are blocked by our opaque on the atmosphere, which is everything in HF. We see at the bottom here, everything roughly below anything longer than 10 meters is opaque to the atmosphere. And then we have a window from 10 meters up to 7 centimeters, roughly, where it starts being attenuated. There's different wells. The wavelengths around everything but blue light gets attenuated. That's why the atmosphere or the sky looks blue. And then, lucky for us, some of the more harmful things, considerable amount of UV and X-rays and gamma rays, also get blocked out. So satellites which observe that gets observed from space. And UHF has UHF frequencies are very small wavelengths, 70 centimeters and smaller. And if we had a look there, they do escape the atmosphere. So generally, UHF, VHF, we only hear local stations, unless they're using a repeater to extend their range. Even then, it's all line of sight. I think we covered pretty much all of that. Whenever a radio wave encounters an obstacle, we don't get it reflected back perfectly. The signal will be weaker on the reflection. Generally because not all the wave is perfectly reflected. Some of it gets absorbed by whatever material. And we call that loss of intensity. Attenuation. Right. And just like light, when a radio wave is reflected on a flat surface anyways, the angle of the incident wave will be the same as the reflected wave. The angle of that incidence is always equal to the angle of reflection. All right. And now that brings us into T3C. We're going to talk about a few other types of atmospheric propagation. VHF signals, like we mentioned earlier, sometimes get refracted under certain atmospheric conditions. And so for VHF, long-distance VHF, which are not line of sight, in dealing with atmospheric conditions, are always reflected by the sporadic E layer. Let's go back to our thing up here, possibly. Sporadic E layer. So the E layer only occurs during daytime, and it's generally easier on our, I think I wrote it up here, on our critical frequency of 50 megahertz, especially, we'll get patches, ionized patches, in the sporadic E layer, which will pop up and go away, which will end up with refractions in our radio waves there. There's also aurora borealis, which is a phenomenon caused by the Earth's magnetic field. Let's see. At its poles, so on and so forth. And auroras can also refract VHF signals. Signals received by auroral propagation or auroral reflection will be very distorted. They are very hard to copy. Because it's so sporadic. If you've ever seen a video of an aurora, they generally aren't a solid color, and they aren't sitting in one place. So the radio waves are going to be exhibit rapid fluctuations in signal strength and be very distorted. That's just a characteristic of aurora propagation. Sporadic E, go back to our diagram here. Sometimes we'll get concentrated patches of stronger than usual E layer. Which will generally affect, cause, go to this color, cause skip on 10 meters, 6 meters, and 2 meters. Generally, this bottom layer is responsible for any, if all, VHF and UHF propagation. And sometimes it's not always the atmosphere that's responsible for carrying radio waves long distances. Sometimes we have, for example, with a mountain, the mountain has a relatively well-defined peak and is sharp. We end up with something called knife edge diffraction, where radio waves will be refracted and bent back we call this knife edge diffraction, excuse me. Now this is a property inherent to all waves, not just radio waves. It also happens with any sort of defined barrier. If you were to have, say, an edge like this, with our radio waves propagating this way, they would hit this barrier, and only the ones in line of sight would continue, but they would be diffracted slightly. And so this way, that's the reason why you can hear stations even if there's no line of sight due to obstructions. And going back to our aurora borealis propagation, another phenomenon which can cause over-the-horizon VHF and UHF communication over vast distances is caused by tropospheric scattering, namely with meteorites. Meteorites, as they are entering the atmosphere, leave an ionizing trail which provides a nice surface for radio waves to be scattered and reflected from. And so we can get pretty good distances with this, something like 300 miles. And the 6-meter band generally is the best for this type of propagation, a meteor scatter. And this is a fairly regular thing. There are fairly regular meteor showers. In addition to our regular D layer, E layer, and F layer propagation, we can also get propagation due to another property of waves in physics, where you have a medium with a different density, two different densities, and a barrier between them. So how am I going to do this? We'll do this. And so we might have an atmospheric layer where there is a section of warm air. Let's see. Warm, moist air. And so the densities between this duct here of warm air in our atmosphere, this is the Earth, we can have our radio waves enter the ducts and bounce around until they reach our receiving station. And these are generally 1,000 feet out. These type of we called temperature inversions, atmospheric temperature inversions, is referred to as causes tropospheric. There we go. and is caused by temperature inversions. Whatever. These can be generally as high up as 1,000 feet or so. And I think that, oh, not quite, almost done with T3. Let's see, go up here. From dawn to shortly after sunset, during periods of high sunspot activity, sunspots are, of course, cause the sun to be cooler and less active. Obviously not the scale. During dawn and sunset, when the D layer, if you remember back here, the D layer is only present during daylight hours. And the E layer as well. So while those are forming, or while those are collapsing, and when there is generally little or lesser excitement from the sun, is generally the best time for long distance propagation in the F layer. So just as the F layer is forming for 10 meters, and that was number 9. Number 10, this is T3C10. We talk about how VHF and UHF is the radio horizon, but I'm sorry, is line of sight. But we call the distance at which two stations can communicate by radio waves the radio horizon. On VHF, UHF, they are line of sight because they get blocked by the curvature of the Earth. But at these frequencies, the Earth is slightly less curved to the radio waves, than it is to light. So generally light will be blocked by the curvature of the Earth before radio waves will on VHF and UHF frequencies. And I can't see the rest of my slides. Where'd you go? So VHF and UHF radio signals travel somewhat further than visual line of sight, simply because of the frequency that they're at. And I think that's it. That concludes T3. We'll go ahead and switch over here to T4. Go ahead and get that covered today. Alright, and I'll switch you back here. Alright, so T4 covers station setup, more of the technical side of things, a little less science, a little more hands-on. Do I have my notes working? Yes, I do. There are many different radio manufacturers, and unfortunately they all haven't agreed on a single standard, and there's really no reason to. A single standard for microphone connectors. And so a microphone from one radio, even though the connector might fit a radio from a different manufacturer, the pinouts might not be the same. And if you make the mistake of using a microphone with the wrong pinout, a lot of microphones are more than just microphones and a switch, but they might also have a voltage supply. I have one right here. Not sure what I did with it. Should probably find it. Here it is. It's got a multitude of buttons on it. So there's it uses one line for signaling. And it is just an RJ45 connector, but this microphone has a different pinout than, say, my, this is an ICOM. It has a different pinout than my Yaesu transceiver, and so this would not work with it in most likelihood. So it's important to be careful connecting up microphones and speaker microphones. Computers have become increasingly important in amateur radio. Computers can be used for generating and decoding Morse code. If you're not proficient at it, it's nice to have something that can copy everything down for you. There's a number of digital modes which use a device called a TNC, which we'll touch on, which can encode and decode digital modes. And we can also use it for logging contacts. Generally, when you've made a contact with someone over HF, especially, you'll give them a signal report. You'll get one back too, and just keep a log to see who you've managed to communicate with. In some cases, it's used in contesting. You can participate in several different contests and then submit your logs at the end of it to be scored. We generally use fairly well-regulated DC power supplies for all communications equipment. It keeps things nice and stable. There's a number of I actually use just a modified ATX PSU. They generally have fairly stable outputs. There's a number of adjustable regulated power supplies for powering transceivers. Filters. You should know what a filter is. Just like a coffee filter prevents large coffee grains from falling through, but water to pass through. Filters in RF can reduce harmonic emissions and attenuate or decrease signals after certain frequencies. So an interesting thing about oscillators is if we were to look at, say, just a wave, and why aren't you working there? There we go. If we were just to have a single wave, we're going to look at it on a Fourier transform. So we're looking at frequency this way and signal strength or amplitude this way. And if we had an oscillator on, let's just put out a single frequency, let's say 5 megahertz, then we would end up with harmonics. It's true of any wave, radio or not. We'd end up with, this is the fundamental, we would end up with a harmonic at 10 megahertz, and again at 15 to be the second harmonic. Third harmonic, and on 20 megahertz, fourth harmonic, and so on and so forth. It would be slightly attenuated as the frequencies increases, but we do need to filter these out. Otherwise, operating on one frequency, you would always cause interference to each harmonic from there on. So most transceivers use filters to reduce these harmonics. For example, we could install a low-pass filter here. So if we only want 5 megahertz output, we can put in a low-pass filter which only allows frequencies below a certain point. We could say, I don't know, 8 megahertz would work. Low pass filter. This would attenuate any frequency above 8 megahertz, whatever it's designed for. And it doesn't completely eliminate harmonics, but what it does is it attenuates it sufficiently that it is near or below the noise floor. such that they don't cause a problem. They're enough of a low frequency. Now, with antenna systems and transmission lines, we'll talk about this. We have, say, a transceiver. And an antenna. Since an antenna is a type of load, we need to make sure that the impedance output of the transceiver matches that of the antenna system and feed line. If they do match, all of the power coming from the radio going into the antenna gets radiated, so all the power is transferred with minimal losses. But if we have a mismatched impedance, then some of that power is going to be radiated, but a majority of it, or a significant amount, will be reflected back. So we have all that power going into our antenna system with a bit coming back. And we measure that efficiency in SWR, or standing wave ratio. A perfectly matched load with the same impedance on either side has a standing wave ratio of 1 to 1. All the power going in gets radiated, and we can measure, the simplest way to measure is in between a transceiver and antenna is to put a device called an SWR meter, aptly named. And all it does is measure the power forward and the amount of power reflected back. I have a picture of it. Here we go. There we are. There's a typical combination SWR and watt meter. It has two needles here crossed. And it will show us the forward power on this scale and the SWR ratio, or the amount of reflected power. Coming back. When we are talking about digital modes, the device which interfaces a computer to a radio is called a TNC, or a terminal node controller. TNC handles. They used to handle everything. You used to be able to hook up just a dumb terminal into a TNC, or a packet modem, and they were pretty clever. Some of these TNCs could run simple bulletin board systems or messaging systems. They could run autonomously without a console attached. And that would be connected between a computer and the radio transceiver. Mostly now, it can be done, the same function of a TNC mostly can be done with a computer sound card. Modem comes from modulator demodulator, and since we're modulating at audio frequencies, it's definitely something a computer sound card can handle. Similarly, they can the microphone port can interface with the receive side of the radio and decode digital modes. Otherwise, a TNC nowadays is used to control the transmit line, the push-to-talk line of radio. But all that can be done just from the sound card with some clever hardware and software. In grounding systems, we want something with a high surface area, flat strap conductor, which is named because it is well, flat. It's generally a rolled flat piece of copper. Sometimes it's also a braid, a copper braid. Those work extremely well for RF grounding systems. And the reason why is because alternating current, especially, the electricity will tend to travel on the surface of the conductor, which is called the skin effect. The high surface area also helps to bleed off static discharges, which prevents static from building up around a setup. It can also it's important to have a common ground point. That way we don't create ground currents and ground loops. Go here. So, for example, we had, oh, I don't know. Come on. There you go. If we have a number of pieces of equipment, let's see. Oops. Let's just say a PSU, power supply unit. We've got a transceiver. We've got, I don't know, an antenna tuning unit, an ATU, and a computer. Ideally, we would want all of these to share a common point ground. These are all connected to earth ground, which is simply a long rod driven into the ground to provide good conductivity with the soil. A lot of people will make the mistake of, instead of using a single grounding point, they'll daisy chain things like this. And we run into issues when back current, which usually will come from our RF source here, we'll end up with, you might end up with a path, for example, the ATU connected to the transceiver here. We can create a path for current to flow. Or between the computer and the transceiver because of, say, if we had a TNC connected, we might end up with current flowing between them, which will introduce all sorts of problems, namely noise. We'll end up with audio noise, whining, horrible audio. So generally you always want a common ground point. Common ground point generally does not create ground loops. These are a few schematic symbols. Earth ground is always this. This is also a grounding symbol. Specifically, it means chassis ground. And for digital circuits and analog circuitry, this will be a signal ground, which will generally be isolated from the chassis or earth ground in order to prevent ground loops. And with our transceiver here, our transceiver might put out a considerable amount of RF energy, and some of that energy can end up flowing back on the shield of a microphone cable, generally to help with interference, to prevent signals from leaking into microphone cables. Good microphone cables are shielded where the conductors inside are surrounded by a foil or a braid, a conductive braid, and that will prevent RF energy, or not RF, but just electromagnetic energy from getting into the cable. But since it is conductive, sometimes we can have RF energy seep out from, say, our transceiver and conduct through the shield and into the microphone, which can cause some noise issues. To prevent that, if you're following my electronics class, we know that a coil, or a a coil, an inductor, blocks alternating current. It also blocks RF energy. So we can make an inductor out of the shield of this cable with a ferrite snap-on core. Got a picture of it here. So here we've got it wound through a microphone cable, and that will choke off the RF, keep it from getting into the more sensitive circuitry. In mobile installations, sometimes you'll hear alternator whine, a high-pitched whine in the transmit audio or in the receive audio. It's bad enough. Which comes from the alternator. The alternator generates an AC current, which gets rectified. But a lot of that can seep into circuitry. Sometimes also engine control units. You've basically got computers nowadays running every small detail inside of a car, and those are generally can be a source of noise. And so to help prevent that noise from getting into our transmit audio, the simplest way to prevent that is by making sure the grounding connection, or the negative connection, is made at the battery or at the engine block. It's generally a good idea to always connect transceiver power directly to a battery. This website here, k0bg.com, provides an excellent guide for installing mobile transceivers. It was an invaluable resource when I was setting mine up. And it'll talk about the importance of fusing and dealing with alternator and ECU wine. There's all sorts of sources of electrical noise that might crop up. For example, I have an issue, I know, with rolling up and down the windows because the motor is not brushless. So when it making contact, that introduces a lot of RF hash, a lot of RF noise into both transmit and receive. Transmitters with gain control on the microphone, volume control, but we call it gain because it's being amplified. Gain set too high can cause distortions, which we call clipping, if it exceeds the zero decibel threshold. It'd also occupy more bandwidth and amplify any noise that the microphone is picking up as well. So it's important to have microphone gain properly adjusted. And when operating VFO, off of a variable frequency oscillator, is basically where you just dial in a specific operating frequency, which can be entered via a VFO knob or typed in on a microphone keypad, or both. Sometimes they're both beneficial. In addition to VFO, we can also store frequencies in memory channels. Generally, most radios and transceivers do have some sort of digital memory in which we can you can store frequencies and label them so that they're easier to remember. And all radio receivers generally will have a squelch control, which silence the background noise you'd normally hear. I don't have a transceiver handy, I don't think. Yeah, I do. But a squelch simply mutes the audio output while there is no signal present. And a lot of HF multimode transceivers have a feature called a noise blinker. Which can significantly reduce static noise introduced by local sources. Generally very handy. Radios, this isn't very common now, but generally multiband and HF radios do all have a RIT control, sometimes called a clarifier. It means receiver incremental tuning or receiver independent tuning. The test will ask you for the exact term, and that's how it's defined by Part 97, is receiver incremental tuning. And it basically allows you to compensate for voice pitch, which would normally be determined by the received frequency. So if a certain station is slightly off frequency, you can adjust the RIT to compensate. But when you go to key the microphone, the transmit frequency will be whatever is dialed in. And this is generally used for narrowband modes, so single sideband, etc. It was originally put in because a lot of transceivers and transmitters had a certain amount of frequency drift. But most everything nowadays has very stable oscillators, and so it's generally not as big of an issue. There are a number of stations with older transceivers for which it can definitely come in handy. And when operating in different modes require different bandwidths. And so we'll generally have a certain amount of filtering capability on the receive side. And by reducing the bandwidth, we can clear up a signal considerably by using whichever bandwidth is appropriate for a certain mode. For example, CW is very narrow band, so it wouldn't make sense for us to cover, 3 kilohertz worth of 3, 4, 5 kilohertz worth of bandwidth on CW if we're only really worried about a single frequency. And that'll help cut down on interference. For single sideband, 2400 hertz is a good bandwidth filter to zero in on a single sideband station. On some radios, the filters have to be physically swapped in, and some have them set up to be variable, and they can be set by a menu option. As I said earlier, for CW, we don't need kilohertz with the bandwidth. 500 hertz is an appropriate filter for receiving on CW. CW is the most narrow band continuous wave, or Morse code, since it's just a single carrier wave being keyed on and off, a single tone. And with repeater operation, repeaters, if we remember, operate, they listen on a frequency different than the frequency they retransmit on. And that difference is referred to as a repeater offset. On 2 meters, the common offset is 600 kilohertz, plus or minus. On UHF, it's a bit wider. It's 5 megahertz, plus or minus. And an audio feature called Automatic Gain Control, or AGC, is used to keep received audio relatively constant. That way loud stations don't overpower your headphones if you got them turned all the way up to hear a station that's a bit more distant. And the distant stations will be amplified as well. Unfortunately, it also amplifies the noise, so it can be a bit difficult at times. And that is all of T4. So we had a bit of a thinner crowd today. I'm hoping some people will watch the recordings. We did pretty good on time. Otherwise, I'll go and wrap it up. And I hope to see you next week, Thursday. We'll do 5 and 6. So, have a good week.